we move on, ladies and gents. We are still on the convection and boundaries PowerPoint. I've realised now I've been doing these videos for a few weeks that the name of the PowerPoint is always shown at the top of the screen. So there you go. Gosh, it took me a long time to realise that, but never mind. So we are trying to understand the plate margins. I've done a video on the divergent margins, and this video is about the convergent margins. There are 3 of them, and they have quite a few similarities, but they have some very important differences. Why are there 3? Well, as we've talked about in previous videos, there are 2 types of crust, and if you look at the title of each of these diagrams, it depends on whether you've got Oceanic-oceanic, Continental-continental, or guess what? Oceanic-continental. And each margin is very much individual, okay? So I'm going to go through each one, but this slide is a little bit of an introduction. If you have continental and oceanic, then you're going to have land, because continental crust is our land that we live on, generally speaking, and you're going to have some ocean. So the first thing is kind of just to think about a map of the world and where you would find land next to the sea. Well, we've just finished the coasts module, so quite often that's a good clue. But what's happening? Well, the oceanic crust is subducted, which is the process of the oceanic crust being forced downwards. And because as it goes downwards, it gets hotter, it begins to melt. That melted oceanic crust then rises, all because of density, and that's where your volcanoes come from. So notice that the volcanoes generally are on land with this one. You get a trench and an accretionary wedge, which I'm going to talk to you more about in a minute. So what's different here, the second one? This time we've got oceanic meeting oceanic. Now, the clue here, folks, is imagine those islands aren't there for a second. There is no land. We've got oceanic crust meeting oceanic crust. We're in the middle of the ocean. So if you've still got a subduction and you've still got melt, and that melt still rises, you get volcanoes. Exactly the same. But look, in this one, the volcanoes generally are on the land. Here, they form islands in the sea. And we're going to look at some examples of that. So that's one kind of big difference, which is where do you tend to find the volcanoes, and do they form new land or not? Here, I guess you could argue they create new land, but they create new land on top of continental crust. Here, you get a brand new island that never existed before. And people do live on those islands, as we will find out. Here, continental, you've got 2 lumps of continental crust. And as we talked about in the structure of the Earth video, continental crust is the least dense material in the Earth, which means you cannot subduct it. It just won't. It's like trying to sink a cork in a cup of water. You are not going to do that. So if you put, this is, if I was face to face with you in class, which I know I'm not, if you hold your hands out in front of you horizontally, fingertips to fingertips, and if you gently force them towards each other, if you cannot go downwards because subduction is not possible, there's only one thing that happens, which is your fingers go up in the air. And that, ladies and gents, is exactly what happens at a continental margin. The 2 lumps of continental crust meet and they create mountains. This is where you get your fold mountains. It is possible to get fold mountains here because the friction between the oceanic crust and the continental means that this bit of continental crust sort of behaves like the crumple zone in a car bonnet. So hopefully you'll never see this in reality, but if someone's in a road traffic collision, the whole point of your car bonnet is to crumple and take the impact of the crash. Well, continental crust sort of does that, and you can, around these volcanoes that you get because of the subduction, you can get fold mountains. So can you see there's similarities, but there's a lot of differences. If you still prefer the old-fashioned terminology, it would be acceptable to call this one and this one destructive, because oceanic crust does technically get destroyed. You absolutely mustn't say that this bottom one is destructive, because nothing gets destroyed. I believe at GCSE they now use the name collision margin, and that would be okay. All right, but ideally we'd like to call them all convergent margins, and it's just the type of crust that changes. Okay, so probably a bit of repetition now. Let's try and figure out what we've got. Well, plate margins should always be very clearly labelled with types of crust and arrows to show direction of movement. So we've got a very good clue here. This is oceanic crust meeting continental. What do we know? Well, we've got ocean above the oceanic crust. We've got land here. We've got volcanoes and mountains. We've talked about that. Brilliant. Trench. So I want to talk more about the trenches and the accretionary wedges. Where the subduction is beginning, you get a very deep part of the ocean called a trench. In fact, I'm going to go forward slightly. The deepest part of the ocean on planet Earth is called the Mariana Trench. You may have heard about it. This graphic makes you realise just how ridiculously deep it is. If you manage to put, clearly this is hypothetical, if you managed to put Everest in the Mariana Trench, you would still have kilometres of water between the top of Everest and the sea. That's how deep the Mariana Trench is. Absolutely bonkers. This diagram is from a different angle, but it gives you the same idea. So here we've got continental crust. Here we've got subduction. It's not a very good diagram, this one. I wouldn't copy this one. And that bit where they meet is the trench. So one of the landforms that you will find at an oceanic-continental margin is a trench. Okay, I'm going to talk to you more about accretionary wedges in just a minute. So why is the oceanic crust subducted? It's denser or heavier. So always come back to density, which we first introduced when we looked at structure of the Earth. The densest things always sink and the lightest things always float. Oceanic crust is denser. It's always the one that's subducted. We've talked about trenches, and I'll pick up on accretionary wedges in a minute. Fold mountains, we've talked about those, sort of bit of a crumple zone. Right, we know that you get volcanoes because as the subducting plate melts, as it goes into the asthenosphere and gets hotter, it will begin to melt, and that's where your volcanic activity comes from. What about the earthquakes and tsunamis? Well, you are going to get a lot of friction here. As this crust goes past this one, that is not going to be a smooth, easy process. This is solid rock moving against solid rock. You are going to get lots and lots of friction and jolting. That is where your earthquake activity comes from, and we'll study this in a lot more detail when we get to the earthquake section. But remember, on average, plates are moving at about 5 to 10 centimetres a year. So there's quite a lot of build-up of tension and friction, and releasing of that is when you get your earthquakes. Tsunamis, right. So, you may recall,
the quake occurred deep beneath the Indian Ocean.
I'm going to pause for a second. You may recall that I said when we did divergent margins, even though the first type of them are under the water, you do not get tsunamis. And that's true. I'm not about to contradict myself. This clip is not brilliant, but there's one little animation.
The juncture of two of the Earth's tectonic plates. The Indian plate has been moving toward the coastal plate for centuries at a rate of 2.5 inches per year. But instead of sliding under, it became stuck. In a matter of seconds, 700 miles of coastal plate shot forward a distance of up to 60 feet.
Okay, so what you need for a what you need for a tsunami is a sudden displacement of a huge amount of water, and it is absolutely possible for that to happen at these plate margins. So because you get your friction and your tension, you get earthquakes. Those earthquakes, if they involve sudden movement to the side or even kind of upward movement, that is called tsunami genesis. It's the creation of a tsunami, and this kind of plate margin is absolutely capable of producing those. So they are pretty deadly things. You get volcanoes, and you get earthquakes, and you get tsunamis. All right. Now, of course, you can pause at any point. Now, let me introduce you to yet another terrible diagram. Brilliant. Accretionary wedge. What on earth is that? Well, let's break it down, first of all, into just some English language words. Accretion is adding together, adding onto. Accretionary, therefore, is something that's kind of added to. A wedge is something that tends to go in a space, in a gap, isn't it? Well, that's kind of what they are. Let me find this. Okay, so can you see in this trench there is a little brown triangle, and that would be made of sediment. Okay, and what I'm trying to show in my horrific diagram is on this bit of crust that is being subducted, there's going to be sand and pieces of shell and bones and all sorts of just stuff on the bottom of the ocean. As that plate gets subducted, this plate is going to scrape all of that off, and it's going to pile it up in the trench, and that is called an accretionary, because it's added to over time, wedge, because it goes in the gap. So it's just an accumulation of stuff, mainly sediment, it has to be said, that gets scraped off the top of the subducting plate. Does it fill the trench? It would never fill the Mariana Trench, that would be nigh on impossible, but certainly it can significantly reduce the depth of the trench. Depends how long it's been happening, depends how much accretion has been happening. All right, so that's them. Oceanic versus oceanic, really there's only one major difference. One major difference. The other one you don't really need to know, and everything else is the same. So the first bullet point, I can't talk, can I? The first bullet point is the one that you don't really need to know. I just thought you might be interested. If you've got two plates of equal density, how do they decide which one gets subducted and which one doesn't? Well, apparently, according to much cleverer people than me, research shows that the one that's moving faster is the one that gets subducted. So you do not need to remember that. I just thought you might be interested. The second bullet point is the absolutely crucial one. So because there is no continental crust involved, if you have two pieces of oceanic crust, then when you have your subduction and your melt and your volcanic activity, you are going to get islands in the middle of the sea, and they generally form a nice little arc shape, sort of a crescent shape. I'm going to show you this on a map. Without the volcanic activity, those islands would not exist. So the islands are volcanoes, and I know it comes as a shock to students usually to find out that people live on active volcanoes, but they very definitely do, and we're going to study a few of them. Everything else, look, we've got our subduction, we've got our earthquakes, we've got our trench, and this one is quite a big accretionary wedge, actually, here. We've got our plates moving towards each other, yada, yada, yada. You're not going to get fold mountains because there's no continental crust, so I suppose technically that would be another small difference. Do not get bogged down in this whole four-arc basin thing. If we were doing short answer questions on tectonics, the questions can get very precise and very specific, but we are not doing short answer questions. We are writing an essay. We want big picture, the kind of key ideas. This is quite a famous island arc. This is the Lesser Antilles, and you will get to know this volcano quite well, the Soufriere Hills volcano on an island called Montserrat. So the idea is, and I know it's weird, these islands would not exist if it wasn't for volcanic activity. They are volcanoes. What often happens is that people forget that they're volcanoes because if there hasn't been an eruption for a few hundred years, or possibly even more than that, people, you know, that the stories don't get passed down the generations for that sort of extent of time. So people can be completely caught unawares by the fact that they're living near a volcano. Montserrat, or sorry, the Soufriere Hills volcano on Montserrat, has rather proved to everybody on the island that it is quite alive, and it's kind of ruined things. So that's going to be one of the case studies for volcanoes. It's a really fascinating case study because volcanic activity that began in the 1990s has pretty much devastated the island, as you can pretty clearly see. Closer, I would love to take you to Montserrat. Nick and I have tried to price up a trip on a number of times, but this, you might actually make it to this volcano. I'm lucky enough to have made it to this volcano. This is Stromboli off Sicily. So if Italy is the boot that's kicking Sicily, just to the north of Sicily there's a group of islands called the Aeolian Islands, and Stromboli is one of them, and you can climb to the top of Stromboli on a guided tour. You can stay in this town. You get there on ferries and stuff. It's quite easy to get to. But look, that whole island that people live on is a volcano. People do live on active volcanoes. I know it's weird. Okay, so we've come to the easiest of the three. Easiest because it's really obviously different, so people don't tend to get too confused. So if we've got two bits of continental crust, as we've said, we cannot get subduction because, and I told you to do that thing with your fingertips, if you've got your fingers pushing towards each other and they can't go down, there's only one possible thing that's going to happen, which is upwards. So you get your mountain building, or if you want to use a posh word, orogeny. No subduction, so if you haven't got subduction, you can't get volcanoes. You can definitely get earthquakes, lots and lots and lots of earthquakes. Fold mountains, you're not going to get tsunamis because guess what, ladies and gents, you are not under the sea, which just reminds me, sorry, going back to this second type, yes to volcanoes, clearly, yes to earthquakes, yes to tsunamis, for exactly the same reason that we said for your first type. All right, it's exactly the same set of processes. Remember, those two have more similarities than they do differences. Sorry about that. Okay, so the best example in the world at the moment of this is, of course, the tallest mountain range in the world, which is the Himalayas. And what's happening is India is forcing its way north into Asia, and as it does that, the Himalayas are being created. It is still moving north, and therefore the Himalayas do get bigger each year, but the increase in size because of plate tectonics gets reduced by weathering and erosion. Not quite cancelled out, but definitely reduced by. So it's all very weird. What we used to have, so apparently, we used to have an ocean between the Indian plate and the Eurasian plate, and it was called the Tethys Ocean. But as and I will remind you, you'll get so fed up of the Wilson cycle soon. But remember, towards the end of the Wilson cycle, the ocean completely disappears and the two bits of continent crash back into each other and create fold mountains. And that's what they believe happened. Because if you did that jigsaw puzzle at the beginning of the course, India did not used to be joined to Asia at all. India was part of Gondwana land, whereas Asia has always been much further north than that. So this little clip, you are just going to watch India crashing into Asia, bum, 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 and you can see the creation of the Himalayas. It's not the best clip you'll ever see, but I was not prepared to draw that one for you. Definitely not. So remember, we definitely cannot call this one a destructive margin. We would have to call this, if you would rather, a collision margin, because that's exactly what's happening. Right, this is the good old Wilson cycle. All right, so we start off with the second type of plate margin we talked about, which is a rift valley, where you've got a lump of continental crust that gets ripped apart. Lots of volcanic activity, lots of earthquakes. This is happening in East Africa right now. Then it becomes our first type of plate margin, where you've got a mid-ocean ridge, which is a big line of volcanoes, and the two bits of continent are getting further and further apart. So those were our two types of divergent margin. Then, over millions of years, your convection currents could quite easily change direction. So now look, this is our third type of margin. We've got continental crust, we've got oceanic crust, we've got subduction, we've got volcanic activity, etc., etc. So all of that ocean, look, that was created is being destroyed again. And I reckon you can imagine or remember what happens next. Eventually, all of that ocean will disappear, and you will get the creation of fold mountains when the two bits of continent career into each other, and that is what's happening in the Himalayas right now. So, I've said to you before, I know I'm a bit of an Alfred Wegener fan, and I'm definitely not about to change that, but J. Tuzo Wilson, who is credited with the theory of plate tectonics, he definitely did bring something to the party. So we're good. I'm just going to check. Yeah, that's right. So this is the end of this video. This is the last slide. Just a reminder, some nice, quite easy diagrams that you could draw for your diagrams here. Right, now, if my explanations haven't been much good to you, please let me apologise. I've heard from all these chats I'm being paused and fast-forwarded and all sorts. Do whatever you need to do, that's fine by me. Please remember to send questions to Nick for his Monday Q&A sessions, but also write it on the last slide of this PowerPoint. There are some hyperlinks to other explanations, and it might just be that the way that another geographer, possibly Nick or possibly someone else, explains it to you, it might just click in your head. So don't just rely on me if I haven't made much sense. I do apologise for that. I do my best, but clearly if you need another explanation, definitely get one. Okay, your final video on plate margins will be next.